We now start chapter 6 module 3 and we will be discussing quadratic forms. After defining quadratic forms, we will see that it naturally gives rise to a symmetric bilinear form and it has its natural occurrence in conics and quadrics. What we mean by that is that the conics can be classified with the help of the theorem that every real symmetric matrix is diagonalizable, and we will also define quadrics and learn a classification theorem. We will avoid a proof here, but we will understand the theorem well with the help of examples. Let us start with the definition of quadratic forms. Let F be a field of characteristic other than 2 and V a vector space over F. Definition: a function q from V to the field F is called a quadratic form if there exists a symmetric bilinear form on V such that q of x is equal to inner product x comma x for all x in V. Once again, the inner product name is being used to call that symbol, but that symbol actually represents a symmetric bilinear form and not necessarily an inner product in the usual sense. Now, given a quadratic form q on V, we can define a symmetric bilinear form in the following way. So, inner product x comma y is given by half times q of x plus y minus qx minus qy. Now, look at that half there, which is nothing but the inverse of the element 2 in the base field F, and it is possible because the characteristic of the field is not 2. We are making an explicit use of that assumption that characteristic of the base field is not 2. Therefore, we see that starting with a symmetric bilinear form, we can define a quadratic form and vice versa, and this therefore creates a 1-1 and on-to correspondence between symmetric bilinear forms and quadratic forms. As the remark says, that it is clear why we need the condition that the characteristic of the field F must be other than 2. Let us look at an example. Let q of x1, x2, xn denote this homogeneous polynomial of degree 2 over f given by summation I is equal to 1 to n aij xi xj. So, xi's are indeterminates, there are n of them, and aij's are the scalars belonging to the base field F. This is an example of a quadratic form, and the corresponding symmetric bilinear form is given by the symmetric matrix whose ijth entry is aii if I is equal to j, and half of aij if I is not equal to j. A particular example, if q of x1 comma x2 comma x3 is given by this homogeneous degree 2 polynomial x1 square minus x2 square plus 4x3 square plus 2x1 x2 minus 6x2 x3, then the symmetric matrix associated to this quadratic form is the matrix A, whose first row is 1 1 0, the second row is 1 minus 1 minus 3, and the third row is 0 minus 3 4. And this naturally defines the symmetric bilinear form associated to Q. And you can see that the principal diagonal entries of the matrix A are nothing but the coefficients of x1 square, that is x1 x1, then x2 square, that is x2 x2, and x3 square, that is x3 x3, and the off diagonal entries are read as, if you look at the 1, 2 position, that is the first row second column position of the matrix, you see the number 1 over there, which is half of the coefficient of that monomial x1 x2. Similarly, if you look at the 2, 3 position in the matrix, that means second row third column, you see the number -3, which is half of the coefficient of the monomial x2 x3, and the position 1, 3 is filled by the number 0, and that is clear because the monomial x1 x3 does not appear in the expression of the polynomial, and therefore the coefficient is 0, and we have the entry 0 at 1, 3 and 3, 1 positions, and the matrix A is symmetric. We have learnt the Sylvester's law of inertia, and we can restate that in terms of quadratic forms, and it says that if q x1 x2 xn given by summation I is equal to 1 to n aii xi square plus 2, then summation over the indices I and j, I less than j, aij xi xj, a quadratic form with real coefficients, then there exists a linear transformation given by y1 is equal to a1 1 x1 etc. up to a1 n xn, then y2 is a2 1 x1 and so on, a2 n xn and so on, yn is equal to an 1 x1 plus etc. up to an n xn, and scalars b1 b2 bn, which can take values 0, 1 or -1 such that q with respect to these new variables y1, y2, yn takes the form b1 y1 square plus b2 y2 square and so on bn yn square. Moreover, the matrix of coefficients can always be chosen to be non-singular, and then the values rank, signature etc. are uniquely determined. Recall that such an expression comes from two things. One is the orthogonal diagonalization of a real symmetric matrix, and the other is choosing a new basis so that we get the desired form. Now, we define a conic which we have seen before in elementary geometry, and we will see that the language of quadratic forms helps us formulate the problems, especially the classification problem for conics. The definition is the following: a conic is the locus of the points in the real plane R2 which satisfy the quadratic equation in two variables given by ax square plus 2bxy plus cy square plus dx plus ey plus f is equal to 0, where a, b, c, d, e, f are real numbers or coefficients. And for spatial choices of the coefficients a, b, c, d, e, f, we get different conic sections. For example, x square plus y square is equal to 1 represents the unit circle, that means the circle centered at the origin 0, 0 of radius 1, whereas x square minus y square is equal to 0 represents a pair of straight lines. The polynomial ax square plus 2bxy plus cy square is called the associated quadratic form of the conic, and this in the matrix notation can be written as this row matrix xy multiplied by this 2 cross 2 real symmetric matrix whose first row is AB and the second row is BC, multiplied by the column matrix xy, which is that good old expression x transpose Ax, such that A is this real symmetric matrix AB BC and X is this column matrix xy. A being real symmetric, it is orthogonally diagonalizable. We may therefore choose an orthogonal matrix Q, which is in fact the basis change matrix, such that the matrix A, that is AB BC, is equal to Q times the diagonal matrix lambda 1 0 0 lambda 2 multiplied by Q inverse, where lambda 1 and lambda 2 are the real eigenvalues of the real symmetric matrix A. Let us write x dash is equal to this column matrix x dash y dash, which is Q transpose X. Then we obtain x transpose Ax is equal to Q x dash transpose A Q x dash, and that is x dash transpose Q transpose A Q times x dash, and that is x dash transpose D x dash, D is that diagonal matrix, and therefore, if we multiply it out, then we get lambda 1 x dash square plus lambda 2 y dash square. Therefore, by using the new coordinates x dash y dash, we have removed the x y term from the associated quadratic form. We know that orthogonal operators on R2 are either rotation or reflection, depending on whether determinant value is plus 1 or minus 1. Therefore, Q being orthogonal, we have determinant of Q is equal to plus minus 1. We can interchange columns of Q if necessary and assume that determinant of Q is plus 1. That means, up to a permutation of the columns, we can assume that Q is a rotation matrix on the real plane. We therefore have an orthogonal matrix Q such that determinant of Q is plus 1, representing a rotation therefore on the real plane, and Q transpose AQ is this 2 cross 2 diagonal matrix lambda 1 0 0 lambda 2. Lambda 1 lambda 2 are nothing but the real eigenvalues of the real symmetric matrix A. Therefore, we have proved the so called principal axis theorem, which says that by a suitable rotation of R2, we can remove the xy term from the associated quadratic form ax square plus 2bxy plus cy square of a conic and obtain lambda 1 x dash square plus lambda 2 y dash square. Let us look at this example. Consider the equation 2x square minus 4xy plus 5y square minus 36 is equal to 0. So, it is a quadratic equation in the variables x and y, therefore, represents a conic in the real plane R2. Here the associated quadratic form is 2x square minus 4xy plus 5y square, and the way we have defined the associated real symmetric matrix is the matrix A, whose first row is 2 and minus 2 and the second row is minus 2 5. Now, the eigenvalues are 1 and 6, that is easy to compute, with associated eigenvectors V1 is equal to 2 1 and V2 is equal to -1 2. And you can see that these two vectors V1 and V2, they form an orthogonal basis for R2. Therefore, after scaling these vectors, we obtain an orthonormal basis for R2 given by these two vectors, the first one being 2 over square root of 5 comma 1 over square root of 5, and the second one is -1 over square root of 5 comma 2 over square root of 5. And therefore, the orthogonal matrix Q, which is the basis change matrix, is nothing but 2 over square root of 5 and -1 over square root of 5 in the first row and 1 over square root of 5 and 2 over square root of 5 in the second row. Note that the matrix Q is orthogonal and determinant of Q is 1. Therefore, it is indeed a rotation of the plane R2, and the change of variables are given by x is equal to q x dash. If we write it explicitly, then it is x is equal to 2 by square root of 5 x dash minus 1 over square root of 5 y dash, and y is equal to 1 over square root of 5 x dash plus 2 over square root of 5 y dash. Therefore, the xy term is removed, and with respect to the new variables x dash y dash, the new quadratic form is x dash square plus 6 y dash square, and the conic is x dash square plus 6 y dash square is equal to 36. We will now generalize the notion of conics in R2 and introduce what is called a quadric. Instead of quadratic polynomial equations in two variables, we will now consider quadratic polynomial equations in n variables, and therefore, the points which would satisfy this polynomial, which is a polynomial of degree 2 in n variables. So, the points would lie in f to the power n, where f is the base field. We will state a classification theorem and see some examples. And what is interesting for quadrics also is that we will be able to define a quadratic form associated to the quadric. We will apply that theorem that every real symmetric matrix is orthogonally diagonalizable, and using that we will be able to simplify the equation defining a quadric. Let us see. Let us now define the notion of a quadric. A quadric is defined as the locus of the quadratic equation in n variables given by f of x1, x2, xn is equal to this double summation over I and j, aij, xi, xj plus summation bk xk plus c is equal to 0. So, the indices I and j and k, they run from 1 to n, that is clear. And this expression is definitely a polynomial in the variables x1, x2, xn, and why we call it a quadratic equation, because it is a polynomial of degree 2, assuming of course at least one aij is not 0. So, you can see the monomials with the largest degree that appear in the expression is of degree 2, they are of the form xi xj, and then there is a linear part, that is summation bk xk, and then there is the degree 0 part, that is the constant c. And once again we can see that there is a quadratic form sitting naturally in this expression, which is coming from that homogeneous degree 2 part, that double summation aij xi xj, which in other words can be written as x transpose Ax, where A is a n cross n real symmetric matrix, and then the linear part is being written as Bx, where B is this row B1, B2, Bn, and x stands for the variables x1, x2, xn, and then the constant c. Therefore, that x transpose Ax is a quadratic form associated to a quadric. Now, this is a classification theorem. Let us state this without proof. So, under the Euclidean group of rigid motions, any quadric in n variables can be transformed into one of the following forms: lambda 1 x1 square etc. up to lambda r xr square plus d wr plus 1, or lambda 1 x1 square plus etc. up to lambda r xr square plus c dash. Here lambda 1 etc. up to lambda r, d and c dash are constants, and x1, x2 and so on up to xr and wr plus 1 are the new set of variables which we use to put that quadric into this form. So, we begin with that fx, which is a degree 2 polynomial. There is that degree 2 part, that is double summation aij xi xj, then the linear part, that is summation bk xk, and then the constant part c, and with new set of variables defined suitably, we can put it into this simpler form. So, you can see that all the terms where the monomials xi xj for I not equal to j appear, they have disappeared now. We only have monomials of the form xi square, and at the most one linear term like d wr plus 1 or a constant term c dash. And what is interesting is that this whole thing can be achieved by rigid motions, that means by orthogonal transformations and translations, because we have already seen that rigid motions are nothing but composition of orthogonal transformations and translations. Let us understand this theorem with the help of a concrete example. Consider the quadric given by this equation 2x1 square plus 6x1 x2 plus 5x2 square minus 2x2 x3 plus 2x3 square plus 3x1 minus 2x2 minus x3 plus 14 is equal to 0. You can see that 2x1 square plus 6x1 x2 plus 5x2 square minus 2x2 x3 plus 2x3 square is the quadratic form associated to this quadric, and then we have the linear part 3x1 minus 2x2 minus x3 and the constant 14. And what is our aim? Our aim is to find a new ordered basis for R3 which represents points of the quadric in simpler form. So, let us begin with this quadratic form associated to this quadric, which is written as q of x1, x2, x3, and you see that homogeneous degree 2 polynomial over there, and that is given by the symmetric matrix whose first row is 2, 3, 0, second row is 3, 5, minus 1, and the third row is 0, minus 1, 2. We know how to write the symmetric matrix out of this quadratic form. The rule is simple. The principal diagonal entries are nothing but the coefficients of x1 square, x2 square and x3 square, namely 2, 5 and 2, and the off diagonal entries are given by the following rule. If you are looking at the ijth position, then look at the monomial xi xj in the expression, look at its coefficient, divide it by 2 and put that number at the ijth position of the matrix, and that naturally gives rise to a real symmetric matrix. Easy computation shows that eigenvalues of A are 2, 7 and 0 with eigenvectors v1, v2, v3 such that v1 is given by this vector 1 by root 10, 0, 3 by root 10, v2 is 3 by root 35, 5 by root 35 and minus 1 by root 35, and v3 is minus 3 by root 14, 2 by root 14 and 1 by root 14. And this is an orthonormal basis for R3. Once we have an orthonormal basis, if we put those vectors in the columns, then that gives a basis change matrix and that will be an orthogonal matrix. So, P is created as the vector v1 sitting in the first column, the vector v2 sitting in the second column and the vector v3 is sitting in the third column. This is an orthogonal basis change matrix. Now, for the point x, if x1, x2, x3 denote its coordinates in the usual coordinate system, in other words with respect to the standard basis, and y1, y2, y3 are the coordinates with respect to the new coordinate system, that is the new orthonormal basis we created with the help of v1, v2, v3. Then with respect to these new coordinates, we can write q as q of y1, y2, y3 is equal to 2y1 square plus 7y2 square. That is clear. That is because these are the non-zero eigenvalues, and therefore, if we apply q d q inverse, then this is the expression that we get. And it is also clear that the new coordinates satisfy these relations, that x1 is y1 by root 10 plus 3y2 by root 35 minus 3y3 by root 14, x2 is 5y2 by root 35 plus 2y3 by root 14, and x3 is 3y1 by root 10 minus y2 by root 35 plus y3 by root 14. Therefore, we get this relationship that 3x1 minus 2x2 minus x3 is minus square root of 14y3. But this is nothing but the linear part of that quadric. Therefore, we have simplified the homogeneous degree 2 part or the quadratic form part to 2y1 square plus 7y2 square, and the linear part has been simplified with respect to the new variables to minus square root of 14 y3, and then there is that constant 14 sitting over there. So, the new expression for the quadric is y3 is equal to square root of 14 by 7 y1 square plus square root of 14 by 2 y2 square plus square root of 14, and this in fact represents an elliptic paraboloid in R3. We have learnt conics and quadrics, their classification theorems, and we have seen some concrete examples. What is interesting is that the main theorem which is being used and which is coming back again and again is that of diagonalizability of a real symmetric matrix, and not just diagonalizability, orthogonal diagonalizability. That means a real symmetric matrix has real eigenvalues and it can be put into the form of a diagonal matrix with the help of orthonormal basis change. And we have learned very important technique of how to put a quadratic form into a simpler expression where we are getting rid of all the terms which contain monomials of the form xi xj for I not equal to j. This gives us a very important application of diagonalization of real symmetric matrices, and it is indeed computable. That is also very important. Of course, the main problem lies in computing the eigenvalues, because in order to compute eigenvalues, we have to solve the characteristic polynomial equation. Barring that, we can find an orthonormal basis and we can explicitly find a simpler form for a quadratic form.